Hello everyone, welcome to our practice lecture about Docker networks. This is Daniel Pinheiro from danielpm1982.com, and in this video we'll put into practice and demonstrate to you all we've learned so far, especially regarding Docker bridge networks that we've seen last lecture. And for that, let me just show you a quick review here. Last lecture we talked a little bit about Docker networks in general, and we saw all the drivers that we may use from Docker default installation, which are the bridge network or driver, the host driver, the overlay driver, the IP VLAN driver, the Mac VLAN driver, and the non-driver or the private driver for no communication at all between the containers. So as we've seen, if you want to communicate between containers, containers are by default isolated from one another, and if you want to communicate between them, for example, for an application in one container to call or to use or to communicate to any other application on the other one, in the examples we've shown so far, for example, for a web application to connect to a DBMS or DB application on the other container, they should communicate. So in order to do that, we should connect them by using a network connected to both. So if you want to communicate between two containers, you should connect both containers to one same Docker network, which may be one of these already available from Docker, or it may be any other custom network or network plugin from third-party vendors or that you eventually create. But regarding the scope of our course, we'll stay with the bridge network because we're working with standalone containers as examples. For example, our springboot application container and our mysql container. They're both standalone containers and not swarm, nodes, or services. So for standalone containers, as well as for single Docker daemon services, we are not using multiple Docker services. We are using only one single Docker daemon service in one same machine, which is our host machine. So for that, the ideal Docker network to use is the bridge one, which is actually the default network that is created when you start your Docker daemon and is automatically binded or attached to any container you create from any image if you do not specify other network drivers or different networks you would wish to attach to that container. So as we saw, we have basically two subtypes of the bridge network, which are the default bridge network, which is the default network for Docker, as I've just mentioned. But we have also another subtype of the bridge network, which is not the default one, which is the user-defined bridge network. So we have the default bridge network and we have the user-defined bridge network. The first one being the default basic network, in case you do not specify otherwise, and the other one being a custom bridge network that you may create how much you want and attach any of those networks to any set of containers in each specific context. So we also saw last lecture regarding specifically the bridge network, the differences between the default and the user-defined bridge network. So as differences between them, we saw that user-defined networks, they do have DNS resolution, which means that you can access from one container the other container by simply using the other container name, which here corresponds to the DNS of the network. So instead of using the IP of that second container, you can simply use its DNS, which in the case is the name of that second container. And then you'll be able to connect either inside applications or at the application.properties file, for example, in a springboot application or in any other application you have inside that first container. On the other hand, if you have a default network, you will not have DNS resolution, and you will have to use manually the IPs from each other container at that same default network you wanna connect. And the only exception, as we also saw, is that in the case that you're using a default bridge network, although it's not a feature of the default bridge network itself, but if you use the link flag or the link feature and create a link between two containers, you also may have the DNS resolution, and even using default bridge networks, you'll also be able to use the name of the containers to communicate with. And that name or DNS will be resolved into the corresponding IP. And why it's so important to have this feature available when using a network between containers? The reason is that the IPs or the IP table that manages the networks, they actually may change each time you, for example, start your system or start your daemon service, or even if you, for example, stop a container, connect other containers, and then try to restart a first container, maybe the IP for that first container will change because you have started other containers, and then you kind of change the sequence of containers started, and with that maybe the IPs of each container will also change. So if you configure an application, for example, a springboot application or the application properties file inside with a manual fixed IP, for example, to accessing the database, maybe that IP will have changed next time you try to run the application or the containers, and then you won't be able to connect to the database container, or even worse, you'll be connecting to a different container with different databases. So that can lead to terrible inconsistencies in your application. So that's why it's so important to use names, because names are unique for each container. You cannot have multiple names running in one same Docker daemon service, for example. So each container will have its unique name, and if instead of the IPs you use the names, you'll be certain that you'll be calling the correct containers regardless the respective IPs have changed. So if you use the name or the DNS, they will always be resolved to the correct IPs of the containers you wanna connect. So again, how do you have this feature available? You have it if you use user-defined bridge networks that we're gonna demonstrate in this lecture, or if you have the containers linked to the default bridge network and you use the link feature or the link flag or the link parameter here, creating a link on top of the default bridge network connection. So always try to use DNS instead of IPs when configuring your applications or the connections between multiple containers. We'll demonstrate that in practice. Also, a second difference is the better isolation you have when you work with custom multiple user-defined bridge networks instead of using for all containers you have one same default bridge network. Not only because of security issues you may have, if you have all the containers you're working in your system for multiple contexts connected to one same default bridge network, every container will have access to all ports of the other container, so it may raise a risk regarding security. And also the other difference related to that is that the configuration you may use to that default bridge network connecting all the containers will be always the same. For example, here it gives us an example of a JSON configuration file for a default bridge network, and you see that you actually can change the configuration to any custom configuration you want by changing, for example, the daemon.json file for the default bridge network. But as you will have all the containers connected to this one and only default bridge network in case you do not use user-defined network. So all the different context containers will all be forced to this same configuration, for example. On the other hand, if you use user-defined network, of course, you will be able to configure each user-defined network the way most adequate for each context, so that you will not be locked up to one and only configuration on that bridge network. You'll have multiple networks, and for each network you will be able to use different configurations. Another difference that will also show you in practice this lecture is how you can connect and disconnect or attach and detach running containers from user-defined networks. So that's one of the features of user-defined networks. You can, without restarting the container or without rerunning that container, you can attach and detach that container to one or more user-defined bridge networks. So we'll prove that to you, how you can, on the fly or with the containers up and running, how you can change the networks those containers are connected to. And one sentence that, in my point of view, doesn't apply anymore, maybe in previous versions of Docker, but for example, first it says here, during a container's lifetime, you can connect or disconnect the container from user-defined networks on the fly. That is true, but in the sequence it says to remove a container from a default bridge network, you need to stop the container and recreate it or rerun it with different network options. So I have tested already, and actually it does not apply, at least to the version of Docker I'm using, which is the latest one. And I'll prove you how you can also, on the fly or with the containers running, connect and disconnect not only to the user-defined bridge networks, but also to the default bridge network as well. So actually this, I believe, I may be wrong, but I believe that this actually is not a difference between a default and a user-defined bridge network, at least anymore, because you'll be able to connect and disconnect to both types of bridge networks on the fly without stopping and restarting the container with different configurations. And I'll show you at our practice how to do that. And at the end of the lecture, we'll get back to links so that I can show you not only about the DNS resolution that links add to the default bridge network if you use the default bridge network along with links, but also the other two basic characteristics of links, which are the environment variable sharing between containers connected through the default bridge network when using links. And we'll also see the automatic generation of environment variables based on each container parameter values, for example, the container name, the container ports, the container IPs, etc. Docker will generate automatically some environment variables and will share those between the containers linked. We'll see that in practice. And finally, the sharing of ports between containers in one same network, either in one same default bridge network or in one same user-defined bridge network. And then we'll also see a little bit more about ports, adding to what we have seen already so far. So this is our quick review. In last lecture, we stopped here before I could show you this third part of the documentation, which is a practice demonstration about how to create containers, connecting them to default bridge network and also to user-defined bridge network for showing at least most of the differences we have seen in theory last lecture. So this lecture will get to our terminal and I'll show you, or I'll implement something similar to what we have here. If it's not the same, it will be very similar to what the Docker documentation exemplifies here at this section, implementing some containers and linking them both to default bridge network and user-defined bridge network. And I'll also leverage those containers we'll create to demonstrate also this fourth part of the documentation, not with the examples here of the documentation, but with the same containers we create for the third part. I'll show you all the documentation shows here regarding links. So if you wanna read about the content of these lectures, you can just go to the documentation and you have everything there very well explained. So let's get to our terminal and start creating our containers, our networks, both default bridge network as well as user-defined bridge networks, and also some links so that I can show you everything that we've been talking about in practice. So let's get to the terminal. And here, let me show you that we have everything cleared regarding our Docker objects. For example, we have no images locally saved. We also have no running containers. We also have no volumes. I have erased all volumes I had here. You can see if you have any volume by using this command, sudo docker volume ls. And also we have no networks different from the 3 network drivers that come by default with Docker, which are the bridge driver or the bridge network, whose name is the same of the driver, bridge. We have the host network by using the host driver, and we have the known name network with a null driver for private isolated containers, in case you wanna isolate the container completely from any communication between containers or even between the container and the localhost machine. So these are the 3 networks that come by default with Docker installation, and the one that we'll be using most is the default bridge network, whose name is also bridge. So in this lecture we'll create other bridge networks or user-defined bridge networks along with some containers, and we'll kind of make a combination of connections to the default bridge network and to the other bridge networks we're gonna create, so that we can see the differences mainly regarding the connections of those containers. But before we actually start creating our networks and containers, let me show you here a quick review about the CLI syntax. For example, remember that we've been using some shortcuts for some operations when using Docker CLI. One of the shortcuts is the sudo docker images command in the plural, and if you remember, that give us the images, the local images we have already downloaded or pulled from, for example, dockerhub. But actually, if we wanna manipulate the image object, the complete command or the original command that exists, it's not actually images in the plural, but the name of the object. And you see that this is kind of a pattern for all Docker objects. That's why I'm showing you now, because we'll have to use that when dealing with network objects. There are no shortcuts, so we have to manipulate them directly and in the complete form. So the complete form is to use sudo docker, the name of the object in the singular, always in the singular, not in the plural. The name of the object, for example, image, and if you want to know the commands you can use for that object, you may use --help, and you have here all the commands that can be used with the image object. And the one, for example, we'll be using is the list and the remove. For example, sudo docker image in the singular space ls, and you can use -a for, if you use the help here also for the ls command of the image object, you see that the -a will show all images, including the intermediate images, which are hidden by default. So for some of the objects you will have this option all, which will show you all of the instances of that object, including the ones that might be hidden. For example, in the case of the image object, the intermediate images. So you can use sudo docker images, which is the shortcut, with or without the -a, or you can use the complete form sudo docker image in the singular, which is the name of the object. Any other command that we saw might be associated with it, for example the list, and the -a also or not for showing the intermediate images. In our case we have no images saved locally, so that's why they're not being shown here. Another example of shortcuts that we've been using a lot is sudo docker ps-a, for example, for showing all containers, including the running containers we have, or the ps command, which will show only the running containers. So if you use this shortcut docker ps, you have only the running containers shown, or if you use with the -a, similar to the images but with a different semantics here, you will have all the containers, including those stopped containers or exited containers, along with the running ones. So for example, sudo docker ps-a, of course we have no containers running or stopped here, but what I want to say is that this is the shortcut, and what's the complete form of this command? It's sudo docker, the name of the object. What is the object name? Container in the singular. And let's see here what other subcommands we may use. We have all these, for example the exec that we have already used, the kill command, the ls command that we've been using a lot, the remove, the start command, and so on. So instead of using sudo docker ps-a, for example, we can use the complete form sudo docker container ls-a, as well as the remove with the name of the container on the side or its ID, and so on. So this is for image and containers. Now what other objects we have? We have, for example, volumes that we have not yet managed directly, but we can, for example, use sudo docker volume, which is the name of the object in the singular, sudo docker volume list, and we have no volume here saved. If you wanna see the other subcommands, also just use --help. You can create a volume, inspect a volume list, prune, and remove. And the objects that we have the biggest interest in this lecture is the network object, which that I know has no shortcut, so we gotta manipulate it in this complete form. Sudo docker network, then we can see the subcommands, which are connect, used to connect a container to a network, the create, for creating the network, the user-defined network, the disconnect, for disconnecting on the fly that network from a container. For example, we can inspect a network Also, you can inspect the container as well. We'll see both cases. We also can list the networks we have. We have already done that. And of course, we can prune and remove any user-defined network we create. So, for listing the networks we have, for example, we saw that by default we have already 3 networks that come with the Docker installation: the bridge default network, the host, and the none or no networks. And we can also create new networks. For example, using sudo docker network create, the driver flag or parameter to specify the value for the driver we want to use, or for setting which type of network we're creating. For example, if we use the driver bridge, we'll be creating a user-defined bridge network. If we used, for example, the driver none, we'll be creating a non-type network, and so on. So let's create now our very first user-defined bridge network by using sudo docker network. For creating a network, the command is create. You should set the driver name. If you do not set the driver name, the default will be the bridge type. So as we are creating user-defined bridge networks, we would not actually have to specify that the driver we want to use is the bridge one. But just to be explicit here, I'll set that, but it's kind of redundant because it's the default driver of the network in case you do not specify otherwise. So sudo docker network create -- driver bridge, and then the name of the network. So I'll set the name as bridge -- DNIOPM 1982, and the name of the network can be any name. It doesn't have to include the driver name, so I'm just including here to but if you don't, you can use any name as the name of the network. Although here at the driver you should use any of the available drivers, either the ones that come with the Docker installation or any other custom driver you may have. So in our case here, it's the bridge driver, and the name of the network will be bridge - DNIOPM 1982. So we've just created one user-defined bridge network, and if we see again sudo docker network, the singular, the list of the networks we have, now we will have the same 3 networks we had from the installation of Docker, which is the default bridge network, as well as the host and the no or none networks. But now we have a 4th network, which is a user-defined bridge network that we can use and even configure with JSON files, but I'll not enter in that. I'll simply want to show you the differences between user-defined bridge networks and default bridge networks. So we have now both networks available, and for creating containers, I'll follow, for example, the image that the Docker documentation uses at that 3rd part. Let me get back here. At this 3rd part, what Docker uses as suggestions here of image is the default all-pin image at the dockerhub, which is a minimum image of Linux that you can use. And in our case here, the image itself, it doesn't matter. What we want to do is to create multiple containers in order to connect them with different networks and show you the characteristics between the connection of those. So it will not matter which image we'll be working with for now. And only on the next lecture is that we'll get back to the Spring Boot application and the MySQL application. But for now, what I just want to show you is an example of multiple containers, and I'll simply use the open suggestion here of image from dockerhub so that I can create these containers and connect a combination of them to our two networks, the default bridge network and the user-defined bridge network we already have. So basically what I'll be doing is exactly what the documentation here suggests, and if you want you can read that at the documentation, but I'll simply do that manually at the terminal. I'll not be reading all of this. I have already read it, so I'll do exactly the same here. For example, for us to create our first container, we will be creating a container and pulling the image from dockerhub, creating the container and running the container, and we will connect that container for now exclusively to the default bridge network. So we'll create a container, an open container from dockerhub, and we'll connect that to the default bridge network here, initially without using links. So we'll create examples not using links as well as using links when connecting to the bridge default network. Let me clear here. For creating that, we can use sudo docker run. The name of the container we'll be creating, let's just call, as the documentation calls, open1. Then we'll set the running of the container as in the detached mode. We'll create many containers running on the background, so initially they'll run in the detached mode, and later we'll attach individually each one that we want to get inside or that we want to manipulate. So firstly we'll create all of them detached, and also we'll set here the iteration mode so that when we attach individually each one we can input and have output from them, and also the T, which is the TTY enabler, so that we can actually see and interact with it by using our terminal here. So D, I, T, D for detached, I for iteration mode, for when we attach individually each container we can interact with. If they were supposed to be running always in the background and not attached to our terminal here, it would not make sense in using the iteration mode or the T from the TTY attachment. We would not need them to be shown at our screen. But in our case, as we'll work with each of those containers both in the detached mode as also each time we manipulate them we'll manually attach them. So in this case it also makes sense in setting in advance the iteration mode and enabling the TTY attachment here. So DIT, and then we'll not use environment variables for now. We'll not use ports for now, the publishing of ports. At the end of this lecture we'll get into ports so that we can explain to you some other features of ports, and we'll not create links for now, but as I said we wanna connect it to one of the networks we have, and the two bridge networks we have are the bridge default network with the name bridge and the user-defined bridge network with the name bridge Daniel PM 1982. So this first one I want to connect with the default bridge network, so I just use here -- network and the name of the network I want to connect, which is the bridge one, which is the default bridge network we have already available. And finally we simply use the name of the image at the dockerhub. And remember that when we created the MySQL container, for example, running in the background, when we want to get into that container, we use the sudo docker exec command with the name of the MySQL container, the -it parameters, and the bash command. So here, not using exec, but using the run statement, we also can set here the name of the command that we wanna call as soon as that container is run. For example, as soon as the open1 container is created from the open image and it runs, I want this command, the hash command, instead of the bash, because at the open installation of Linux, it's a minimum installation, so it has simpler commands, in this case the hash command. I also want this command to be run as soon as the container runs. So instead of running the container and only later calling the exec command, I'll be calling, as the documentation also calls, directly here at the run command. You can do that. You can run the image by creating and running a container, and right after the image name you can also pass here the name of the commands internally to that container that you want to call as soon as the container runs. So with that, we don't have to use the exec command to get into the container as soon as it is attached to the execution of our terminal. So we simply pass it right after here the image name, and it will be executed this command right after the container is initiated. So enter. So it will pull the image and it will create and run the container with these characteristics set here. So as we want to test the connection between two containers, initially I'll create a second container called open2 with the exact other same parameter values. The only thing that I changed was the name of the container from open1 to open2, so that we now will have two containers linked to the same default bridge network, not to the user-defined network, but to the default bridge network, and running the same image, and the image won't matter because we're just testing the connection between them, but also initially detached. We can attach it later, each one, when we want to manipulate them, with the iteration mode on, and with the TTY having as a screen this terminal here, and also with the hash command here at the end as the initial command running as soon as the container runs. So enter. So it's created the second container, and if we use, for example, sudo docker ps-a or container-a ls-a, we'll have both containers, open1 and open2, up and running at the background or as daemon services detached from our execution here, although we can attach them manually, and we'll do that in a second, so that from inside one container we can connect to the other. But before that, let me show you another feature Docker CLI has, which is sudo docker inspect. I guess we have not yet used this command so far, but we'll be using a lot here, because we may inspect basically here in these examples two things. We may inspect any of the networks. Actually, we can inspect any Docker object, but in this case we want to inspect the networks we'll be using, and we also can inspect the containers themselves. So first let's inspect the bridge default network, whose name is bridge. So after the inspect here, you use the name of the instance of that object type. In this case, the object is network, but the name of the object we want to inspect is bridge. Bridge is the name of the network object, which is the default bridge network we can, for example, inspect. And with that, we can see in a JSON format here all the characteristics of that default bridge network. For example, the name of the bridge network, which is also bridge. The default one is bridge. Its ID. Every object instance in Docker has a hash ID. We can refer to it specifically through its name, which is the most common the easiest to do, or we can refer to it by using its ID. So we have other information about its creation, when it was created. Scope, it's a local and not remote. The driver, it's the bridge driver, the same driver that our user-defined bridge network also is. So we have a bridge driver for the bridge named network, which is the default one, and we have the same bridge driver for our user-defined bridge network, which is the bridge-danielpm1982 that we'll inspect in a moment. Now we are inspecting the default one, whose name is bridge. We also have other information as the gateway to our host machine. We have here some options. For example, if it's the default bridge, and it's not a user-defined one, it's the default one. Enable ICC, enable IP, masquerade, and some other low-level configuration features that we can set using JSON files. But most importantly here, what we want to see when we inspect each of the networks we'll be working with are the containers connected to that network. So if we see here, we have not only the gateway to the host machine from that network, but we have all the containers connected to that bridge named network, which are the two containers we just created, the open1 and the open2, both connected to the same default bridge network. And here for the open1, we have its IP address inside that default bridge network connect to our local host machine. So the IP for the open1, at least for this initiation of the Docker daemon service, as we said, this IP may change if we start disconnecting and connecting multiple containers in different sequences. The IPs will be different, but in this instantiation and for these containers already running, the IP for the open1 container is 172.17.0.2, and for the open2, its IP address is 172.17.0.3. It's not actually wise to use IPs at the configurations for the connections inside our applications. For example, at our springboot application, we did not use IPs. We used the DNS, in that case for our MySQL container, and not the IP. So we used the name of the MySQL container, which in this case is the DNS. And for that, we gotta have the DNS resolution habilitated as we had at that context. For example, remember that we used the links exactly for having that feature enabled for using, instead of the IP, using the MySQL container name as the DNS for connecting the Spring Boot container to the MySQL container at the application.properties file. So here we are not using links. So we'll prove now that if we get into open1 and we try to access open2, we'll be able to do it, but only if we use open2 IP. We also prove that if we use the name of open2, it won't have the DNS resolution, and Docker won't be able to know which IP is that. It won't resolve this DNS name to this IP. Why? Because we are using default bridge network and we are not using links. So this is the first example that I want to show you. Before that, let me show you that we can also inspect, sudo docker inspect the container, sudo docker inspect, and here you can use the container name or the ID, open2 for example. You can inspect each container individually, not only the network but the containers. And we also have a lot of information about that individual container, including here at the network settings, the networks that we have linked to that container. We will see that we can connect multiple networks to each container. In this case, we have only one network, which is the default bridge network connected to it. And here we have the IP address of that container. So as you can see, we can look for the IPs we have for each container manually by inspecting either the network or the containers directly, or also we can do that by entering inside the container and using a Linux command called IP address show. But that's only if we are inside the containers by using the exec command and the name of the command and the bash command, or in this case the hash command, or can now simply attach each container we wanna manipulate. So we could have used the docker sudo docker exec command, the name of the container, and the hash instead of the bash, because there's no bash in the Alpine installation or the Alpine image, but it has the hash, which is kind of similar. So if we call it as this, and before that we gotta use the IT as well, we will do exactly the same. You can see that we are inside the Alpine 1 container now. Let me exit. We'll do exactly the same as we call, in this case, sudo docker attach Alpine 1. So two ways of getting to Alpine 1 container with the exec command, or attaching a DIT or detached iteration T2I enabled container with the hash command already called at the running of that container, so that now that we are inside the Alpine 1 container, we can test calling the other container, the Alpine 2 container, so that we can see that we can reach if that second container network is reachable from this first container. So we are inside the Alpine 1 container, and we will test now to access the Alpine 2 container network. That in this case, as we saw, is the same network, the default bridge network called bridge. So for checking if the connection is available, the simpler way is to use the ping command. It's a Linux command, ping. We can use the -c with the value 2 for ping twice instead of keep pinging indefinitely. We just need, for example, 2 pings to confirm that the connection is available. Ping -c2 and the name of the IP or the DNS that we want to connect. So as we saw, if we try to access the DNS Alpine 2, the DNS here being the name of the container that we want to connect, we will not be able to reach it or to resolve this DNS to an actual IP, and it will say that it's a bad address. Why? Because we are using default bridge networks without links. So there's no DNS resolution here in this context. And if I wanna test the connection, actually we can reach Alpine 2, but we have to use its IP instead of the name of the container. So I don't remember the IP. How to get that? We gotta get out the Alpine 1 container. And for getting out, if you simply exit, it will not only exit but stop the container. I don't wanna stop the container. I wanna have all the containers running so that we can test the connections. If the container is in the exited status, it won't be reachable by any other container or from the host. So you gotta keep all of them up and running. So how to exit from inside a Docker container without stopping the container? You simply use the Ctrl P and Ctrl-Q shortcut instead of using exit. So we got out the container, but the container keeps running. So that if you use, for example, ps-a, you have here the open1 container still running in the background or in the detached mode. So first it was in the detached mode, then we attached it, we got into it, and later we changed it to the detached mode again, so that it keeps running in the background, but we are not attached to it anymore at the execution here at our terminal. So now we can use sudo docker inspect again for our open2, because we need the IP of that container to test the connection from the open1 container. And let me just copy here the IP address of the open2. Okay, and now we can attach again to open1 and get into it, and now we can call ping-c2, and as there's no DNS resolution, we gotta use the IP of the open2 container, which is 172.17.03. And through that, if the open2 container, which should be reachable through this IP, is running and available and connected to a reachable network regarding this open1 container, we'll have a success in the ping from this first container to this second container. So let's press enter, and now we see that our test was successful and that all packets were sent and received with 0 packet loss. So differently from the case where we use the DNS or the open2 container name, which we failed to connect when using the IP for the open2 container from the open1 container, we were able to prove that the connection is reachable. And now what I want to show you is that if we had to create the open2 container with not only linked to the same default bridge network of open1, but also linked with the link flag or the link parameter from the second one to the first one, having as source container the open1 and as recipient container the open2, then we would be able to use the DNS resolution even when using only default bridge network. So let us create again. Let's stop the open2 container and I'll erase it, and then I'll recreate it using the link flag or the link parameter as we have already used before. So for stopping a container, you can simply use container stop and the name of the container open2, or you could erase it by using rm-f, but I'll first stop it for then removing it. Okay, now for removing it's the same but using rm. Okay, if we try to see now the available containers, we only have the open1, and what I want to do now is to recreate the same open2 container. Let me get here the run statement open2, also with the date flags or parameters, setting as network the same default bridge network, the name of the image, the hash command, initial command. But in this case, right before or in any place before the image name, we will be creating a link from this open2 container to the source container, which will be the open1 container, and using as alias for that link for any name here, for example open2 open1 DNP-2. So we have, it's the same way we used to create a link between the springboot container and the MySQL container. Now we are linking using also the default bridge network, these two containers, the open2 container to the open1 container by using the link flag here. So here Docker says links are only supported for user-defined networks. Actually, it's not true, but in this case it's because they have updated this part of the CLI syntax when you explicitly use the network as bridge, and they do not let you create links for bridge network if you explicitly set the default bridge network as the network for that container. But if you do not explicitly set it, for example, if you just erase here the network, it will automatically connect that to the default bridge network the same way, but now it will let you create the link so that now we have the two containers connected to the same default bridge network, but now with the link flag enabled. And what does that change? What we are doing? The first thing that I want to show you now is simply the DNS resolution. So as we created a link having as source the open1 and as recipient the open2, the DNS resolution that we have is from inside open2, so we gotta attach not the open1 but the open2 container, and from here we can see that now we can reach open1 container from open2 but using open1 DNS, because now we will have DNS resolution even when using exclusively the default bridge network, because now we have links. So there you have, all packets were sent and all packets received with 0 packet loss. So now we can ping or connect from open2 to open1, both using the IP as using also the name of the container, which in this case is the DNS of that network connection. So let me get out here, and just for showing you, one of the disadvantages of links is that if you wanna access in both ways, you will have to create both links. So if we get into open1, we will still not be able to call the open2 by using the open2 container name. We will not have the DNS resolution. Why? Because we only have the DNS resolution from the recipient container to the source container. And as the link we created had the open2 as the recipient container and the open1 as the source container actually won't even know that the link exists. The link will work only for the recipient container. So if we wanted to call open2 from open1, actually we would have to have open1 as the recipient and open2 as the source. But we can actually still read open2 by using its IP, as they are both in the same network. So with this, we proved how we can connect two containers by connecting them through one same network, in this case the default bridge network, and how we can use the IP as eventually the DNS or the container name of those containers in case we use the link flag while using the default bridge network. Or next we'll see that for user-defined bridge network we won't have to use the link, and still we'll be able to have DNS resolution the same way we had here when using links. So now what we have to do is to create a third container that we're gonna call open3, and we'll link that third container not to the default bridge network called bridge, but to the user-defined bridge network that we have already created and that is already available, named bridge-DanielPM1982. So let's do something similar to the creation of open2, but using open3. We'll also use the same detached iteration mode and TTY enabled. We'll not use links. As I have already mentioned, you only should use links if you're using the default bridge network, because it won't have any advantage to create a link when using user-defined network, because you will already have the DNS resolution by default, so you should not use links. But we gotta set the network now. We can't omit that, because if we simply do not specify any network, what will happen is that the open3 container will be created but connected to the same default bridge network we already had connected to open1 and 2. So now, as we want to connect to a user-defined bridge network differently from the default one, we gotta specify that by using the network parameter here, and as value the name of the user-defined bridge network, that in our case is bridge-danielpm1982. So with this, we create an open3 container connected not to the default bridge network, but to the user-defined bridge network called bridge-danielpm1982. And for connecting to this open3 container, we'll test that we cannot connect from the open3 to either open1 or open2 if open1 and open2 are not connected to this user-defined bridge network. Because for two containers to connect, remember that they gotta be connected at least to one same bridge network. They may connect to more than one, but at least to the same one, they gotta be connected. And as the open3 is connected only to the user-defined bridge network called bridge-danielpm1982, and open1 and open2 are not connected, either of them, to this user-defined bridge network, so it's impossible to connect from either those two open1 and open2 containers to the open3. So instead of creating an open4 container with the same definitions here of open3, what I want to show you now is how you can change the network attached to a container, either adding more than one networks to that networks already connected to that container, or removing existing networks and adding different ones. So for this, I'll take the open1 container, sudo docker inspect open1. If we inspect it, we can see that the only network which open1 connects to is the default bridge network. So how can we do to make a connection between open1 that only is connected to a default bridge network to open3, which is connected to a user-defined bridge network? For now, they can't communicate because they are linked to different networks and have no network in common between them. But we can either remove the default bridge network from open1, and I'll show you it is possible even on the fly without stopping the container, differently from what the documentation says. But for now, I'll simply add a second network to open1 to also show you that you can have multiple networks connected to one same container. So how we can add a network to a running container on the fly? Sudo docker network is the Docker object name. Sudo docker network connect the name of the network we want to connect, bridge-danielpm1982. It's the user-defined bridge network. And lastly, the name of the container we're connecting to. So sudo docker network connect bridge-danielpm1982 to open1. This way, open1 will both be connected to the default bridge network as to the user-defined bridge network called bridge-danielpm1982, which is the same of open3, and thus open1 will be now connectable or communicatable to open3. Enter. And now if we inspect open1, we'll see that it's now connected to both bridge networks, the default bridge network through this IP address, as well as to the user-defined bridge network through this other IP. So let me copy this one, because this is the IP that we gotta use if we want to connect using the IP from both containers, open1 and open3. We gotta use the IP from the same network common to the two containers we want to communicate. For example, if we use the IP that open1 has at the default bridge network, it will continue not to be able to be reachable from open3. But if we use the IP of the user-defined bridge network of open1 now, we will be able to connect that from open3. So this is the IP we gotta use, the IP from the same user-defined bridge network that also is connected to open3. So let's copy that. And now we can either go to open1 and ping open3, or we can get into open3 and ping open1. So let's prove that we can communicate both ways. And now not only through the IP, but through the DNS, as now we are using a user-defined bridge network which by default has the feature of DNS resolution, even without using links. So we have no links between open1 and open3, neither in one way or in the other, but we have a common user-defined bridge network connected to both. So we'll be able to ping open3 from open1, and we'll also be able to ping open1 from open3, either using their respective IP from that specific user-defined bridge network as their DNS or container names. So let's sudo docker attach open1 and try to ping 2 times open3. Let me do already through the DNS or the container name, as we know that we have by default the feature of DNS resolution when using user-defined bridge network. So we do not need to specify the IP, we can simply specify the unique and always constant container name. So this name will never change, so it's much more secure to use DNS or the container names instead of using IPs. Why? Because the IPs may change, while the container names will never change. So especially from inside application configuration files, always prefer to refer to containers not through their IPs but through their DNS or container names. So let's ping from open1 the open3 container using the user-defined bridge network. Okay, successfully connected and with 0 packet loss. So again, we do not have any link flag between open3 to open1 and not from open1 to open3. But we are now using user-defined bridge network, so we have by default DNS resolution, and that's why we can call from one container to another. We can communicate using not the IPs but the DNS or the container names. The same we can do if we attach open3 to our terminal and try to ping 2 times open1. It also communicates successfully even without links or link flags set between those 2 containers. But what happens now if we try, for example, to communicate between open3 and open2? So let's go, first let me copy the IP of open2, as we know that from the DNS it won't recognize open2 because there's no DNS resolution here with open2, because open2 is only connected to the default bridge network and there's no link having as recipient the open3. So open3 will not know the DNS of open2, but eventually it could know the IP of open2 if connected to the same network, which is not the case here. So I'll prove now that open2 cannot connect to open3 and vice versa, because open2 is connected only to the default bridge network, differently from open1, which is connected to both, and open3 also is connected only to another bridge in different network, which is the user-defined bridge network. So if we get into either one of them, either open2 or open3, will not be able to connect from one to another, either using the DNS or even the IP. For knowing the IP, we can inspect the container or even the network, or we can use an exec command, for example, sudo docker exec. If you want to know the open3 IP address show, using the iteration mode and the TTY to the current terminal. So the first connection here is the IP to the loopback device. Do not consider that. Consider starting from the second connection here. So for open3, its IP connected to the user-defined bridge network is this one, 172.19.02. So with that copied, sudo docker, we can now attach open2 and try to ping twice from open2 to open3, but using its IP. So again, open2 is in a different network from open3, and there is no common network between those two containers. So if we try to ping from one to another, the communication will fail. 100% packet loss. The other way around, first, if we looked up the open2 IP, and the open2, remember, is connected only to the default bridge network with this IP. Let's copy that. And now let's attach open3 instead. Here we attached open2 and try to access open3. Now we'll attach open3 and try to ping open2. And the same way we'll not be able to communicate. Why? Because there's no single and common network between those two containers. So with this, we tested creating specific networks, both default bridge network and user-defined bridge network. We learned how to connect those networks to a container, either at the running statement as using the network object command, connect, for example. Also, we learned and proved that we can have more than one network connected to a container. For example, in the case of open1, we connected both to the default bridge network as to the user-defined bridge network, and that's how we managed to connect from open1 to open3, because at least we had one common network between them. And also we proved that if two containers have no common network between them, they won't be able to communicate, for example, between open2 and open3. And we also, in the case of open1 and open2, we managed to use open1 as the source and open2 as the recipient container for a link between open2 and open1 for adding the feature of DNS resolution, even when those two containers were connected exclusively to the default bridge network. Also, we proved that we do have the DNS resolution even without the link flag or the link parameter if we have a connection of type user bridge network, as in the case of OP1 and OP3, so that we are able to connect by using not only the IP, which we should not, because the IP may change, but the DNS, because we will have by default, when using user default bridge network, the DNS resolution, so we can use the DNS or the container name of each container to communicate between them. We also saw that we're able to alter the connections or the networks of a container, for example, OP1, without even stopping that container. It's called on the fly. So on the fly, we can alter the networks that one container is connected to. For example, OP1, if we see, for example, we can inspect, for example, OP1 sudo docker inspect OP1. We see that it's connected to both networks. And now let me prove you not only that we can connect, but that we can disconnect a container from a network on the fly. And that not only applies to user-defined bridge network, we can disconnect, for example, this network here from OP1, but also that we actually can both connect and disconnect from a default bridge network without stopping and rerunning the container. So for proving that, let's just disconnect from the default bridge network of this first container, and later we will simply connect again. So have in mind it's a default bridge network, and we will do all this on the fly. How can we disconnect? The same way that we can connect, sudo docker network, which is the name of the Docker object, sudo docker network. The subcommand is now disconnect. The name of the network we want to disconnect is the bridge now, it's the default one. And the container we want to disconnect from is the OP1. So this will disconnect the bridge default network called bridge from OP1, letting it connected with only the user-defined bridge network called bridge-dnopm-2. So as you can see, if we inspect OP1 again, we now see that at networks here, we only have the user-defined bridge network and not the bridge default bridge network anymore. So we have disconnected on the fly a container from a default bridge network, as we can also do for a user-defined bridge network. For example, we could disconnect also the bridge DNOPM-2 network from OP1, and if we inspect it now, it won't have any networks connected to it. So, and if you see sudo docker ps-a, OP1 is still running, up and running, and we have not stopped the container, either for connecting a second network or for disconnecting both the default bridge network as the user-defined bridge network from this up and running container. So not only we can do that on the fly for user-defined bridge network, but also for the default bridge network, at least in this version of Docker, sudo docker version 20.10.17. So at least in this version we can on the fly connect and disconnect networks, both default bridge type as the user-defined bridge type. So now let me reconnect at least one of the networks to OP1. Have in mind that if OP1 is not connected to the default bridge network, not only OP3 but also OP2 won't be able to connect to OP1. So instead of connecting now to the default, I'll connect to the private network or the non-network, just for showing you how to connect to a different driver network. We already have the non-network available. Sudo docker network ls. So we already have here ready the available the known network that we can use. So let's use it as an example of a different driver network instead of the bridge driver networks we've used so far, the default and the user-defined bridge network. Let's now add to open1 the non-named node driver network. So we do exactly the same, sudo docker network connect the name and not the driver name, the name of the network we want to connect, in this case the known network, and then the name of the container we want to connect that network to. So with this, if we now inspect open1, we can see that the only network connected to it is the known network. And when a container is connected to the non-driver network, basically it's completely disconnected both from all other containers. It's completely isolated both from all other containers as from also the host machine. For example, now I'm at the host machine at my machine OS outside Docker. So let me get the IP of open1 sudo docker exec open1 IP address show. If you see here, and also if we inspect open1 sudo docker inspect, we can see that we won't even have an IP for open1 anymore. Why? Because at the known network we do not have an IP address. If you see here, there's no IP address at the known network, so we can't even try to ping that from the host machine, for example. We won't even have the IP of the open1 anymore. There's no sense in using the old IPs from when open1 was connected to other networks, because those IPs do not exist anymore, because those networks also do not exist anymore here, connected here to open1. They exist connected to the other containers, but not to the open1. So the IP for those networks at open1 have disappeared, and now we have no IP that we could use even for trying to connect. So in how we can now make open1 connectable again, we can add one or both bridge networks again. In our case, we have the known network connected to open1, and when the known network is connected to a container, you cannot add multiple networks. So we first gotta remove the known network from open1, and then we can connect any other number of networks, including one or both bridge networks we have here available. So sudo docker network remove the known network from open1. Actually, not remove, we are not excluding the network, we are disconnecting it. The remove command would be if we wanted to remove the network, and as this is a kind of default network for the Docker installation, we cannot remove it. We could remove, for example, the user-defined bridge network that we created, but what I want to do is not remove. What I want to do is simply to disconnect that known network from open1, so that we connect one or more other networks. So sudo docker network disconnect known from open1. Okay, it is disconnected. If we see now, we still have no IP because we have no network connected. But now that we have no network connected, including the known network, now we can use sudo docker network connect, for example, the bridge default bridge network to open1 again. And if you see now the IP address of open1, we now have the IP again for open1 through that default bridge network. And in this case, if you see, it's exactly the same, but only because we had not added, for example, that open1 container to other networks before adding to the default bridge one here. So it kind of follows a sequence number, the IP, so that's why it can change depending on what sequence you use to change those networks and containers connected to those. You will have different sequences and maybe different IP numbers, but in this case here we still have the same IP number that we had for Open1. And let me just copy that. And for proving that it's now connectable again, let's attach again sudo docker attach open2 and try to ping open1 again. And as in this case we have a link from open2 to open1, we can use the DNS resolution or the IP, and both works even at the default bridge network. Why? Because we're using a link from open2 to open1. So now we go to our last part of this lecture, which is this fourth section of the Docker documentation that I want to show you, which is again about links. But part of it we have already seen, which is the DNS resolution that links guarantee when we're using the default bridge network. So we won't have to see that again. We have already seen. Then the documentation here shows a little bit about the different forms we have for publishing a port. Then how to use links, and this we already know, the syntax for adding a link for the communication of two containers, one being the source and the other being the recipient for that link. And lastly, we'll have a little bit talking about environment variables and both the sharing of those variables between the linked containers as the automatic creation of variables based on certain data about one of the containers, specifically the source one, and the sharing of that to the recipient one, so that the recipient one will have access to some of the data of the source one from using environment variables. And the second way for data to be shared between linked containers is the /etc/hosts file, which is a file related to links. But and then we end this section. So let's go to our terminal, and first we'll see a little bit of ports and how we can declare ports when running or creating a container, and why it talks about ports in a link section. Basically because the ports will be one of the data that will be able to be shared between linked containers through the automatic created environment variables. Both the name of the variables and the values of those variables will be based, for example, on the ports that a certain container exposes. And also remember that two things also important about ports is that at least in linked containers the ports are shared without even being published, and also in user-defined bridge networks also the ports are shared between the same user-defined network. So all containers in that network, they share their ports without also you having to publish them. And that's actually quite a big advantage both for user-defined networks as well as for default bridge networks when using links, because if you do not publish a port, for example, this port will not be able to be accessed from outside Docker, and that will add some level of security to your application. So In case we only need to use ports between Docker containers in one same Docker daemon service. We do not have to publish those ports. I have already discussed a little bit about it because we may either use a user-defined bridge network or we may use links. And either way, all ports from any of the containers connected to one same network will be exposed to all the other containers in that same network. So we won't need to use, for example, the -p in those cases. And actually, that's one of the changes that we're gonna do in our code. For example, for the MySQL container, we will not expose anymore those ports 3306 and 33060 because we won't need that container to be accessed from outside Docker, and that container will only be accessible through the same default bridge network using links, or after we'll create user-defined bridge network to do the same connection between the Springboot application and the MySQL container. So either way, the ports will be automatically exposed between those two containers without we having to expose those ports to the external environment. So remember that, that's one of the advantages of links as well as of user-defined bridge networks. And the other advantage is the sharing of data between two linked containers by using environment variables that we already know that are shared between the source container to the recipient container if they are linked in a default bridge network, as well as some data also in the /etc/hosts file, which also share data between the source and the recipient containers if they are linked. And also remember that if you're using user-defined bridge network, which is the advisable to do, preferably you would be using always user-defined bridge network if you were using bridge networks. But if you use user-defined bridge networks, have in mind that you won't be able to have this automatic creation of variables, let alone the sharing of data between the linked containers. Even if you use links in a user-defined bridge network, you won't have this feature available there, including also the /etc/host file with the same data. So this environment variable automatic creation and sharing, as well as this sharing of data also through this /etc/hosts file, is exclusively for links when used along with default bridge networks. But in case you decide to use user-defined bridge network, which is the most modern way of using the bridge network, you have other strategies to sharing data also, for example, by using volumes for both containers with configuration files and all of that. Another way is using swarms. We are not using swarm here, but if you use swarm, you will be able to share data through the swarm platform. And another way that we will be using on the next lecture is by using Docker Compose for running all your containers at once and also share any environment variables in them. So if you use Docker Compose, even if you're using user-defined bridge networks, you will be able to share those variables as we are sharing when using default bridge networks along with links. So let's get to our terminal and first make a quick review about how to expose and publish ports. So here at the terminal, I have already erased all the containers we had, as well as the images, and we also do not have volumes, as well as the networks we have now is the bridge network, which is the default bridge network we have. I erased or removed the other one we had, the user-defined bridge network, because we won't be using user-defined bridge network in this lecture anymore. to demonstrate the links features, we gotta use only a default bridge network. So we will only be using this network during the rest of this lecture. And we also want to be using the host and on networks, only the bridge one. So the image also won't matter, so I'll keep using the same open image that we used before, because what matters to us now is still the syntax about how we can manage these objects, as well as the links and ports. So regarding ports, let's make here a quick review. For example, you know that we only can declare a port or set a port at the running statement. So it's not a manageable independent object that we can set separately and later attach to a running container, differently from the networks, volumes, and so on. So if you run a container, pulling the image from dockerhub, creating the container and running that container, and you do not specify any publishing of any port, at least for networks outside that same network where the container is created, as well as for outside the Docker environment, you won't have any ports published, and you won't publish anymore any ports for that container. So you would have to remove that container and create another container, and then publishing the ports you need in case that container should expose and publish any ports to the outside world or to any different network than that network where the container would be. So we always gotta set the port at the running statement of the container, because those ports are only created and set to the container at the creation of the container. So let's use a basic example here, how to create a container from the open image using as entry point the hash command, setting as the name open1 as we were doing. I'll not set the networks because by default we can use the default bridge network anyway, so we do not have to specify that. It's redundant to explicitly, for example, set here the network as bridge, because that will already be the network set if we do not specify otherwise. So, and that's exactly the network we will be using for using links, because we gotta use the default bridge network for that. So sudo docker name open1, the name of the image and the entry point command, and here we can publish or set the port we want to publish the way we were doing before. For example, if we publish like this, we'll be exposing and publishing the internal 80 port from any image that has that port to the outside 80 port in our local system or in our host. So this is the easiest way of exposing and publishing a port. If you use as here the -p, then on the right of the column the internal port of that container, and at the left of the column the port outside the container, and in this case actually at the host operating system we're using. So I'm exposing here. Suppose that open would have this port to expose and to be used by external applications. So we would be exposing and publishing the internal 80 port from the open container, the open1 container, and mapping that to our host 80 port outside Docker daemon. So with that, we would be able to access any server, for example, listening in this port inside that image we are creating the container from. Suppose that this would be an image with a server, for example, a database server or a Tomcat server, listening to this port, and as this port is mapped to this other port at our operating system, we would be able to access from our operating system this outside port, and with that the requests and responses would be mapped to and from the internal port of the container as well. So we would not be accessing the internal port of the container directly. We would be accessing through the application, the external application, the outside port, and that outside port would be mapped to the internal port of the container. So this is the way we were doing, but actually we can also, for example, we can set a range of ports. For example, we could set a range of ports at our operating system between 49,152 until the last possible port we could set, which will be the 65,535, and map any of these ports available and dynamically selected to the internal port with some service listening inside the container. So what this will do is to automatically select between this range of ports, any of these, and map that to the internal port 80 of the container. And what's the advantage of that? Instead of using a fixed port, in some cases that will be the most interesting to do because it avoids that a set port here at the operating system would be, for example, not available, and eventually we could not implement the connection from our operating system to the internal port of the container because the outside port would be occupied. So if, for example, the system tries to allocate one of these ports and it's occupied by some other application running in our operating system, it just selects another one, but always within this range that we've set here, and then it maps the same way to the fixed port here inside. So this is the range declaration of a port, an outside port, to an internal port of a container. Another way in using the same -p parameter here is that not only we can set the range of the outside port that will be mapped to the fixed internal port of a container, but we also can set the host, for example, the IP of our localhost column, the port of our host outside, and column the internal port again. So now we have two columns. Always on the right of the last column it will be set the internal port inside the container, and on the left it will be set the fixed port that we want to map, or a range of ports that the system may select within that range. And also, when specifying the host, we can also set here on the right of the first column the IP of the host that we are authorizing to access that internal port. So if we do not specify here the IP of the host that will be using that port, it may be possible, for example, to any host, including any external host, to access through any of those mapped ports the container and eventually any critical information or data of that container. And of course, this is a very critical security issue that can be minimized by specifying exactly not only the port that we are mapping outside to this internal port, but the exact host IP, and only that host will be able to access that mapping between the external port and the internal port of that container. So I almost forgot here the run command, and for this image we also should not forget to set the running as dit, as we have already explained before. So sudo docker run, the name open1, the dit, and the port having as only authorized IP host, the 127.0.0.1, which is our local host. Only this host can access the port that is going to be published, which will be chosen dynamically from within this range of ports that we have set, and that will be mapped to the 80 port inside the open1 container. So let's press enter. Okay, and now in order that we can check if any port within this range has actually been published and mapped to this internal port for specifically this host, we can simply use sudo docker ps-a, and here you have the container created, open1, it's up and running. And remember that the ports are only opened in case the container is up and running. For example, if we stopped that, we would have blanked values here for the ports, but as it's up and running, so the ports are connected and published, not only published but also connected according to the mapping here above. So the internal 80 TCP port from inside the open1 container is mapped to this external operating system port, which was in turn selected from within this range of ports that we have set. So here above we wouldn't know which port would be selected, but we can see that the port selected within this range that we've set has been the 49,158 port number. And also here on the left we have the only host IP that is able to use this operating system port to get into our container through its 80 port mapping. And another way that we could see that is by using sudo docker port and the name of the container, open1. So here is the same thing that we have here above when listing the containers. So we have the internal 80 TCP port from inside the container mapped to the 49,150 port. So no other IP other than this one will be able to use our operating system 49,150 port to access this internal port, port 80, at our up and running container. Another test that I wanna show you is that if we stop the containers, sudo docker stop open1. Okay, we have stopped open1, and if we try to see again, sudo docker ps-a, you have blank values here for the ports available because the container is not running anymore. It's at the exited status. So when a container is stopped, it stops publishing or it stops exposing any port. So any previous publishing that we had set will be eliminated until we start again that container. So let's start it again. Sudo docker start open1, and if we see again the available containers running, so here it is again up and running, and also with some port here published, exposed and published, mapped to the internal 80 TCP port at our exact localhost IP address. But if you see here, the port now is not the 49,158, it's another port, 49,159. So that's the advantage of using range for the outside ports that we are mapping the internal ports to. Why? Because if in any case that the ports that we would be setting as fixed port, for example, would be occupied, the system simply chooses another port from within the many ports range that we have set, and we won't risk not having the application running because of lack of that specific port if we had used a fixed port here. If any other application was using that port, if we had used only one port here, then the application wouldn't be able to run because that port would be occupied. But in case of ranged ports, the system simply chooses the first available port that it finds dynamically, and we won't worry that some fixed port would be occupied and avoid our container to start. And also, as you see, it does change the ports that are chosen within that range. Although the IP that we set here as a fixed authorized IP won't change, only this IP will be able to access the and also the exposed ports inside the Docker container won't change. So what changes is only the port, the external port of the operating system that is being chosen from within this range. So another way that we have to do something similar to what we have done here is, for example, we can keep using the localhost IP as a fixed IP, authorized IP, but we could also change here and let range empty, so that also the system would choose within all available ports any port that is available and that it finds. So let's run this for showing that we can leave this port value here, the outside port, empty, so that Docker daemon service can choose any port in our operating system regardless any preset value or even range value as we did before. So we gotta remove the container first. So sudo docker container remove, and the name of the container open1. It's running, so we gotta use the -f to force it to stop and later being removed. Okay, now it's removed, and now we can recreate it. Remember that for changing the ports values, we gotta recreate the container from the image again. So let's recreate with this setting here, leaving blank the outside port number here, and see what happens. Okay, now sudo docker ps-a. If we see, it has the same way chosen within the ephemeral range of ports. If you wanna see the 3 categories of ports that are available in operating system, you can read about it. We have 3 categories of ports. First, we have the first category, which is the well-known ports, which are within the port 0 and the port 1023. So these ports within this range between 0 and 1023 are called well-known ports or system ports that are exclusively for the operating system to use. Then the second category of ports we have is the registered ports or user ports that go from 1024 until 49.151. And the third and last category of ports that we have in any operating system goes from 49.152 until the last possible port, which is 65.535. So this last third category is called ephemeral ports or dynamic or private ports, because they are short-lived ports that are only selected or reserved for a short period of time, and then they are liberated again for other applications to reuse them. If you want to read more about it, you can search for it. But in this case here, that we do not set any value here at the host port to which we are mapping the internal port, the range will be the ephemeral range, and that's why the port selected here in our last example was the 49.153. So, in one last way of using ports that I want to show you, first let me remove again the open1 container. The other way that we can declare ports is by, instead of using the lowercase p, the dash lowercase p, we can use the dash uppercase p. And through this parameter, it's the more generic way of declaring. It will choose any port for any host IP and for any declared port inside the container. So let's try this and see what happens. And nothing happens. Do you guess why? The container is up and running, so every port declared inside that image open should have been exposed here dynamically to any selected port available by using this dash uppercase P. But why none have been selected? Because this image open actually doesn't expose any port by default in its Docker file. So if you simply use the dash uppercase P, it won't find any port being defaultly exposed in the Docker file, and therefore no port will be automatically exposed here as well, even with the container running. So in the case a Docker file of an image that you're creating a container from doesn't expose in the Docker file the ports that you want, you gotta not use the dash uppercase P, but if you wanna publish any port, even not declared at the Docker file, you gotta use the dash lowercase p instead. So these are the many ways that the Docker documentation shows us how to use ports. And now we can go back to links and try to create some containers, some linked containers, and show you the automatic creation of environment variables and also the automatic sharing of data through using these shared variables as well as the /etc/hosts file. And one of the data of the containers that will be used will be the ports exposed and published. So now that we know all the ways to publish ports, we can go back to links and see those two other characteristics of links that we have not yet seen, other than the DNS resolution that we have already demonstrated. So let me clear again every object, and actually let me also show you here how you can remove objects from Docker. We have already shown you some shortcuts, for example sudo docker system prune -a. You can use this, but in this case it will not stop the containers, it will only remove the containers that are already stopped. So you would have first to stop the running containers. For example, the open1 container is running. It wouldn't be erased if you simply used directly the system prune -a. So you would have to use sudo docker stop or container stop, it's the same, open1, and later use the system prune command in order to remove this one container, or in the case of many containers you would have to stop all those and later use the prune as well. So what other way we have to remove containers? First you have the container remove, which is only also for stopped containers, but you can also use the -f option here to force the stopping of the container and then the removal of that. So sudo docker container rm-f, and the name of the container, this would remove this one container here. But also if you had more containers, for example, let me just create another container here, open2, just to have two containers available. Let's suppose you would have 20 containers and you wouldn't want to use the system prune, or even you wouldn't want to go one by one, stopping those, for then being able to use the system prune or the remove, the container remove. So how we can remove and stop at once a list of containers, we can use sudo docker container remove, or we can first stop, but as we can use remove directly with the -f, we'll simply do that, sudo docker container remove -f, and then we would put here the name of the containers, but in our example, as we would have many containers, we would have much work to use the same command 20 times. So instead of that, for calling any docker command on a list of objects, you can use this $sign and the opening parentheses, and then sudo docker, and any command that returns a list of objects, in this case of container objects. So how you can return the list of containers, ps-a, or container list -a. In order to retrieve only the values, we also gotta use here the not only the -a but the -q as well. So you pass here a command that returns a list of the respective Docker object that we wanna, for example, remove, and always on the right we pass the -q. We can pass it separately or together with the last argument here, it doesn't matter, and then this will return the list of containers we have. This expression then will be converted into a list of instances of containers that then can be removed, because here on the right of the remove command we can pass only one container, for example, or one container space another container space another container, and that's what this expression will return. It will return a list of containers, and those will then be able to be removed through the container remove command here. So let's do that, and you'll see that both containers, or if we had 20 containers here, will be removed at once. Okay, both containers are removed. If we try to see again sudo docker ps-a, there's no container running anymore, but you see that it doesn't return the headers as well. So, and this also apply, for example, for images, sudo docker image remove, and then suppose we had many images, we could use here the $sign and open and close parentheses, and inside any expression of docker CLI that would return a list value of image objects. So sudo docker, it could be images, which is the shortcut -aq, or it could be image list -aq. So the same way, if we use this command, this expression will return a list of all images available, and the remove image command from the image object will remove all those at once. So let's try that. Okay, all the images removed. The same also applies, for example, for not the RMI but the RM, for networks. If we use the network object, sudo docker network remove, and here sudo docker network list, and in the case of network there's no -a, but we should use the -q as well. We only have 3 networks. If we, for example, use sudo docker network ls, we only have these 3 networks, and neither of them can be removed. But in case we had any user-defined network, for example, it would have been removed through this command and expression. Let's just test here, as we have 3 object instances here of the network. Let's try to demonstrate here the -q, sudo docker network ls-q, and you see that it returns the IDs, the same IDs that we have here for the network IDs, of the 3 values of networks that we have without returning the headers and also without returning the other values here, because for removing or for stopping, in the case of containers, we only need the IDs. So the -q will return the IDs of all that type of objects without returning other values. So that's why we use it here, because we only should pass either the name of the objects or the IDs. And we can also do the same for volumes. So we can, if we had many volumes in our machine, we could delete all of them by using sudo docker volume remove, then the IDs of volumes we had, or the names of the volumes we had. For example, a similar expression, sudo docker volume ls volume. Also, there's no -a for it, so we would only use the -q. And if we had any volume here returning from this list, one or more, these volumes would be removed also at once. So when this message here appear saying that at least one argument should be passed, and when we have used this expression here with the $sign and the 2 parentheses returning a list of IDs of that specified object, in the case that this list doesn't return any value, then it will complain that we have not passed any value, because this list actually has returned a null value, as we have no volume saved locally. So that's why it's returning this message. But it's quite alright, because if we had any volume, this would work. And if it doesn't work, it's because there's no value to be removed. So this is all the syntax we need for removing all the objects. And don't forget that if we have all the containers stopped, we can stop also the same way we can remove all at once. We can use the sudo docker system prune and -a for removing at once all the stopped containers, not the running ones. So we should stop first all the containers, then all the networks not used by any running containers. So that's why we also should stop the containers, because if we have any running container, not only the container won't be removed, but the networks connected to that container also as a security measure here won't be removed. And in the case of images, the same. If we have any container created from a certain image, that image won't be removed if the container is running. So these are the forms that we can remove or stop or list many Docker object instances at once. So now we have no containers, no images, no networks. Actually, we have only the default networks here, the default bridge network, the host, and the none, but no user-defined network, and also no volumes. Okay, and now we'll start demonstrating some links examples similar to the ones we have already used with the open image, so that we can also show you how environment variables can be automatically generated from the container's data and shared from the source to the recipient, linked containers, as well as how they are not only shared, but also can be used in the applications running at the recipient without even we have to reset them again. So, and also finally we will see what that has to do with the etc/hosts file. So that will be critical for us to find a more elegant way to run our original containers, the springboot container and the mysql container, because we have both for now running at a default bridge network using links, and we are not leveraging everything that Linux gives us in terms of reusing parameterized data and automatic environment variable generation and sharing. And actually we've been redundant in the environment variables that we have set at the running commands of those two containers. So in order for me to be able to show you a better way of using the run command for linked containers, we gotta see here now how environment variables are automatically created and how they are automatically shared, even without any ports being published and without explicit setting of these environment variables, because they will be automatically generated and automatically shared from the source to the recipient linked containers. And also the etc/hosts file that is managed both automatically as also can be managed manually, for example, for sharing that data between the source and the recipient containers. So let's start with our examples and conclude this part of networks and links. So two ways that linked containers run on default bridge networks have to communicate or to share data between them automatically is environment variables as well as the etc/hosts file. So we'll see both of them as a way that linked containers have to automatically share data, metadata or custom data set at environment variables, for example, between them, between the source container and the target container or the recipient container, so that the recipient container will have a lot of automatically generated variables, both the name of the variables as the values of those variables will be automatically generated from the metadata or the data, custom data set at the source container. So that, for example, if the recipient container wanna establish a connection or configure a connection to the source container, for example, suppose the target or recipient container is a web application, as in our case, our springboot application, and the source container is the DB application. So dynamically, based on the data of the source container, the target or recipient container will have shared with it a lot of automatically generated variables with some values also automatically set from that other container, that source container, in order that it can use those values and those environment variables to, for example, connect to the source container without us even having to set any environment variable on this target or recipient container, because all the data needed, all the values needed will be already available through these automatically created and set variables from the source container that the recipient and target container will have access. So another thing that the documentation also says is that all environment variables originated from Docker within a container are made available to any other container linked to it. So not only because the network will be always the default bridge network, but because if we have more than one or actually more than two containers linked within themselves, so all the variables from the source container will be available to the other containers linked to it, and all of them also connected to one same network, which is the default bridge network. So you gotta analyze if this is actually what you want to do, to share all the variables and metadata values or custom values from the source container through these automatic generated environment variables to all in any other container linked to it. So now let's see what's the pattern of creation of the names of those environment variables that are automatically created at the recipient or target container based on the data of a source container. Let's see how their names are constructed automatically by Docker. What's the pattern that Docker uses to construct the names? Have in mind that we are not setting any environment variable manually. These are all automatically generated variables. So how Docker uses and which data Docker uses from the source container to create at the target or the recipient container these environment variables automatically, and what values Docker also sets automatically in these variables from the source container data. So basically the main source of this data that Docker uses to set these variables and to construct the name of these environment variables automatically generated are, for example, the env command data set at the Docker file. So remember that at Docker file, one of the many commands that we can use there is the env command, so that we can, at the image Docker file, already set environment variables for the container to have when run from that image. So that's one of the sources of information that Docker will take to create these environment variables. The env command at the Docker file of the source container. Always remember that we're talking about a source container and a recipient or target container. And the source container is the one that will be the source of information for the creation of the environment variables at the target or recipient container. So the env commands at the Docker file of the source container, not the recipient one, but the source container, will be one of the sources of data or metadata or custom data set at those environment variables at the Docker file for some of the environment variables created at the target or recipient side. And another source is the environment variables that we create at the run command. For example, with the -e, the --env, and the -env file, in case we have some file with environment variables that we take. For example, Docker Engine can take a file with a lot of variables to create when running or creating a container through the run command. So these are the main sources of data from the source command used to create these automatically generated environment variables at the target or recipient container. So observe that both the env commands and data, as well as the -e, -env, and the -env file, they are all related to the source container. So it's easy to remember because the source container, the name already says that it's the source of data to the recipient containers, including in this data the environment variables automatically generated by Docker that will take data from these information of the source container and turn that data into environment variables at the other container or the container linked to this source one. So these environment variables enable programmatic discovery from within the target container of information related to the source container. That's what we said. At runtime, even if these data change at the source, the container that will be created as the target one and linked to the source will, at runtime, take this data to generate these environment variables. So these environment variables enable programmatic discovery from within the target container of information related to the source container. So at runtime, the target container will be able to get information from the source container and programmatically discover that data and turn that available through these environment variables to the target or recipient container. So, but how the name of these environment variables are constructed or mounted, there's a pattern for that, and we will see each pattern for each environment variable automatically created. The first pattern is this one. One of the automatically generated environment variables at the target container based on the source container data will be this one, constructed with the alias of the link connection underline the word name. So I'll just explain how each of these variables are constructed, and later we'll see that running on the terminal with some sample containers. So the first variable that we can consider is this, created from the alias of the link that we are using among those two linked containers. For example, if the link alias is webdb, so this environment variable here will be automatically generated taking the alias that we have here, for example webdb, underline the word name, and then it will set as value for that specific environment variable a slash and the name of the recipient container or target container, and slash and the name of the connection, so that we can see that at this path that the recipient container is connected to the link taken by this alias here, webdb. Also, other environment variables always automatically created are for each exposed port from the source container, not from the target, from the source container. Each port that the source container exposes and or publishes, each port will receive or will have created 3 environment variables for each exposed port with this pattern here. The alias name, for example in this case here webdb, the alias name underline port, underline the number of the port exposed, underline the protocol TCP or UDP of that exposed port. So this will be a base pattern that Docker will use to generate 3 environment variables for each port. So it will take this format here and add to it 3 different suffixes. For example, the address suffix, the port suffix, and the proto suffix. So Docker will take this base pattern here. For example, for this alias webdb, Docker will take webdb port, the number of the port, for example 5432, and the protocol TCP, and add to that for each one of these 3 environment variables for each exposed port 3 different words. The first one, the address, the second, the port, and the third, protocol. So for the first one, we would have, for this example, the webdb port 5432 TCP and the address. And here we would have the source IP address, while in the port environment variable we would have the number of the port, and at the proto variable we would have the string name of the protocol. So all of these variables, as you see, can be used, for example, in the configuration of our web applications for dynamically discover these values from a source container, and that source container, for example, a database container that web application would be connecting. So at runtime, a web application, for example, would have available all these data automatically from the source and would be able to connect and discover the values for each of these variables. So at the configuration we would, for example, simply use the variable names, while the variable values would be automatically set at runtime. So this is the main advantage of these environment variables from the link option of the default bridge network that we can use at the run command. Another environment variable that's created other than the alias name format and the name port, ports protocol, along with address, ports, and proto, is the alias underline port environment variable, which is similar to this other one here, alias name, but instead of alias name, it's the alias port. So for this example, in which the alias is webdb, it will be constructed as webdb underline port, and the value for it would be the protocol of the connection of that link, and the value for it would be a URL containing the protocol / the IP and the first exposed port. And as first it explains that it would be the lowest number port. For example, if we had more than one port exposed, this environment variable would have as value the value of the lowest number port to create this specific environment variable with the alias underline port. So in this case, it will be TCP : the IP of the source container the port with the lowest number. And finally, Docker also will take each environment variable, as we've already said, declared or used at the source container, and we'll use that to create environment variables also at the target containers, along with all these other ones already mentioned here above. So for each environment variable at the source container, Docker will create a respective environment variable at the target container or the recipient container using this format or pattern here, with the alias of the link connection underline env underline the name of the environment variable at the source container. So, for example, we could have one or more environment variables at the source container, so Docker would take each one of these and create environment variables at the target one, but using different names, starting with the alias of the link that we set when running the target container. So that's why it's so important, the alias of the link connection, because as you see here, automatically generated environment variables at the target will be created taking this alias name as part of the name of the new environment variables created at the target container from this data at the source. So if you, for example, change that alias after having set your whole web application for using those environment variables when running a new target container, for example, if you remove the first one and run another one, changing that alias, so Docker also will change the environment variables created automatically and at your application. For example, at the application.properties file at your springboot application, you will have environment variables names that will not match anymore with the ones that actually are created from Docker, because Docker will create from a different alias, and of course most of the environment variables will have their names changed at runtime because of that, and of course that won't match anymore the configurations at the application.properties file of the Spring Boot application you had previously set. So have great careful regarding that. And if we for some reason do want to change the alias name, we gotta know that first, if we do not want to introduce any configuration problem between the two containers, the web application container and the DBMS container, we gotta also change those environment variables if used at the application.properties file of the Spring Boot application, for example. If you change the alias, you also will have all or most of these variables changed, the name of those variables, if not also the values, but including the names, and you will have to update all the names that you eventually had used at the application.properties file, for example. So that's why it's pretty important to understand how these environment variables are created so that you may avoid making these mistakes. So for every environment variable at the source, you will have the alias name underline env underline the name of the environment of the source set as an environment variable also at the target container. So these are all the environment variables that are created. Let us quickly review here. We have the alias underline name format. We have the alias underline port format. We have the alias underline env underline the env name format for every environment at the source. And we have at least 3 other ones for each of the ports as the format, the name of the alias. Here it has put as name, but it should have been put as alias also. The alias name underline port underline the port that those 3 environment variables refer to, 3 for each port, and the protocol associated to that port. So as you see, it's not actually most of the environment variables that use the alias name. It's actually all automatically created environment variables at the target linked to the source one. All of them will use the alias, either this alias underline name, this alias underline port, this alias underline env underline the name of the env, and also this one, the name of the alias underline port underline the port number underline the protocol type. So all of them will begin with the alias that we have set for the link between those 2 containers, the recipient or target container and the source container. So, and how we can see these variables after they are created. After we run a container, we simply can use the env command. Here the documentation shows us using that env command as the entry point here of a sample container from a sample image. So as soon as the container is created, it calls the env command inside, and that will list all those automatically created environment variables. We'll show all those variables at the target, which also you see start all of them from the link alias. We have the alias name, alias port number and protocol, underline proto, port and address, and alias port number and protocol without the proto, port and address here with the complete URL. So all of these variables you gotta keep in mind that will be turned available at the target container linked to the source one. At the source, we will already have all those data available, either from environment variables set at that source container or from the ports that it exposes and already are also set there at the source itself and so on. So what it's being turned available now is that all of this information from the source will be also available at the recipient or target container through these automatically generated and automatically set environment variables at the target container, at the recipient container, so that the recipient container will leverage from this information to not only have detected at runtime all of these data, but also to be able to configure, for example, a connection without having to set necessarily these environment variables as we were doing in our first example. So the way I said that we would be using a more elegant way to work with links is that instead of setting all of these environment variables or some of these at the target container that is linked to a source container, we will simply make use of these automatically generated variables in a parameterized way without having to manually set the values, because the values will be automatically discovered at runtime when the connection is set between those two containers. So we'll mostly now work with parameters, taking these values names instead of setting manually the values, and let these values to be discovered at runtime. So it's a much better way of working, for example, with our Spring Boot container, because now we won't bother, in case those values change at the source, at the MySQL container, we won't bother to have to update them at the application.properties, because there we'll only be using the environment variables names and not the values directly. And unless we change the link alias or the exposed ports from the MySQL container, environment variables names won't change. So it's always better to work with unchangeable parameter names or constants instead of the values directly, because we won't have to update every time those values eventually change. So we automate all the discovery of those values from the source, and we work simply with the also automatically created environment variables, which in this case won't change unless we change the link alias or the ports at the source, or so on. But it's a much more elegant way to work with links by leveraging all this automatic parameterization and the discovery of the values from the source to the target container through these environment variables created by the Docker engine. So, and as we've already said, another way of sharing those information from the source to the recipient containers is the /etc/hosts file. And one big difference here between those environment variables and this file is that this file will be always updated with the values, while those environment variables may not be. It says here, unlike host entries at the /etc/host file, IP addresses stored in the environment variables are not automatically updated if the source container is restarted. For example, if we also taking the example of a web application as the recipient and the DB as the source. If we restart the DB, those environment variables already created from the source at the recipient container, they will not be updated if any value is changed at the source. Only if we also remove or recreate the recipient container as well after restarting the source. So there is the risk that we have these values changed, the IPs or the ports at the source, and if the recipient container is already running and with those environment variables values already set from the first running of the source container, there will be a serious inconsistency between those two. And that does not occur at the /etc/host file. So the documentation also recommends that for resolving IP addresses, we should use preferably not the environment variables, but the /etc/host file, because we have guaranteed that in that file all the IPs, for example, will be updated regardless of how many times we have restarted the source, or regardless of any change those data may have had at the source container after the recipient container already had those environment variables created and set. So, but before we discuss a little bit more about the etc/hosts file, let's go to our practice and practice for some sample containers the creation and check the availability of these automatically generated environment variables here according to these patterns that we have learned through the documentation. So here again at the terminal, back to our practice, remember that we have cleared all objects. For example, we do not have volumes, we do not have images, we do not have containers, and the only networks we have are the standard ones that already come with Docker installation, including the only one that we will be using, which is the bridge default one. So let's use here the same open image we've used in the last examples. I just want to show you the constructor of these automatically generated environment variables at the target container, taking the information from the source container to generate automatically and also to discover those values at the target side. So for that, we simply have to create two containers, one linked to the other, and then list the environment variables or recipient container. Remembering that all these variables we have discussed will be set as variables of the target container and not at the source. The source won't even know that these environment variables exist, unless we also create a link not at the recipient only, but also at the source, so that the source also turns out to be a recipient, and the other container, which once was the recipient, will also be the source for the other one, so that we have this change of data and information with the creation of these automatically generated environment variables on both sides and in both ways. But to simplify things, let's just create one recipient container and a source container, and we'll see that we'll have these variables generated at the target container or recipient container based on the information of the source one. So let's first create the source container. Sudo docker run -dit --name open. Let me change here to open source. This will be the source container. Sudo docker run name open source -dit. The network will not set, so as default it will be set as the default bridge network, and the link, and also the link will not create at the source, will create at the recipient, run it, so we have no link here. We simply have now the open image name and the entry point that I'll keep using the hash. Actually, I'll create another source container, open source 2, and for this one I will also publish some ports here. For example, -p 8080. I'll not set the IP as fixed for the host, and also not use a range of ports at the host. I'll just use the simplest example we have used so far. And what I want to also create is a sample environment variable here at the source, so that you see that it is taken to create the environment variables at the target container. So -e, and the name of this environment variable will be env1. Okay, so this first source container I created without exposing any port and also without any environment variable, but here in the second source container I did create both the exposing of the port as well as the environment variable here at the source, so that we can see if all the expected variables at the target container are actually created from all these information. So let's create the second source container. Okay, now we gotta create the target container. Sudo docker run name open target or open recipient dash dit. Here I'll not expose any ports. I just want to see if the ports of the source container will be detected here by the discovery of the values for the automatically generated environment variables at the target, but we don't need to expose any port here at the target. We will eventually make use of the values of this port at the source, but not at the target. We also do not have to create any environment variable here at the target. We are just testing if the environment variables at the source will be detected and automatically created at the target, but we do not need to create any environment variable here at the target. But what we do need to create here is, of course, the link between this recipient target container and the other two source containers. And for that we use the dash link flag at the run command of the target container, the name of the source container. First let's link to the open source, which is the first one we've created up here. So, and then the very important value, which is the name of the alias of the link. And as we saw, all the automatically generated variables will start with this name. So let's set it as open link. So every environment variable automatically generated taking information from these two source containers, after we also will be linking to this other one, all this information will be the base for the creation of these automatically generated environment variables at the target container, and all of them will start with this alias name here, open link. And then we gotta set here the image name and also the entry point comment. So I guess we only need these. Oops, my bad here. Just remember that the link flag must have two dashes. Okay, now we've created the target container that already is linked to that first source container, and all those automatically generated environment variables must already have been created by the Docker engine from the information of that source container and set or saved those variables at the target container itself. So remember that these variables are not saved at the source, they are saved at the target, because at the source we already have those information. So the object here is to transfer that data from the source to the target. So that's why those environment variables are created at the target site. So and how we can see if those variables have been created at the target container? Well, we can, for example, in this case, we can attach sudo docker attach the open target container, open target, so that now we are inside, because we are using as entry point here the hash command. So as the container runs, it also executes the hash shell command of the open Linux distribution inside that container, and as we attach that container to our terminal, we automatically enter through that hash entry point command to inside that open target container. So now that we are inside the open target container, we can use the Linux env command to see all the variables inside that container. So as you can see here, all these environment variables here have nothing to do with Docker. These are environment variables from the Linux distribution, the open distribution inside the container. They were already here, and as we can see here, the only environment variable automatically created from the source information we had at this target container is the environment variable based on this format here, the alias underline name. So we have here the alias of the link, which is open link. If you see here, the alias we set at the link is open link. So this environment variable starts with open link underline name, and the value set here is a path containing the target container name, which is open target slash the link alias, again open link. So for the first source container, this is the only environment variable automatically generated by Docker inside our target container. So why is that? Because we have not published or exposed any port or any environment variable here at the source, the first source container. So as we have no port exposed and no environment variable declared at the source, the only environment variable created by Docker at the target will be the environment variable taking the alias underline name, having as values the target container name and the link name or alias through which it's set to the source container. So this is the case in which we have no ports and no envs declared at the source. So now let's do another thing here. For example, let's remove the open target container so that we can rerun it or recreate it, and now setting as source container not the first source container but the second one, in which we'll have some ports exposed and an environment variable here also declared at the source. So for recreating, we gotta remove it using the -f so that it first stops and then removes. Okay, and now we can recreate it using exactly the same running line except for the source container name, which will be open source -2. So now we are linking this target container not to the first source container but to the second one, on which we have ports and environment variables declared. And let's see now if we have different results here regarding the environment variables created by Docker from that information from this other source container. So enter. Okay, it's created, and now let's get into it. The automatically generated variables must already have been created, so we just gotta get into and see which environment variables we have. Sudo docker attach open target container, and here we simply use the env command. Okay, and now we not only have the only generated environment variable that we had in the first case, using the alias underline name with the target container name slash the link alias, but we also have many other environment variables, because now we have a port being exposed at the source and also an environment variable exposed or set there. So for example, this other pattern here, alias underline port, now we have port, it's this one, it's not in order, so we gotta have a little work to identify the ones we wanna find. So open link, which is the alias underline port. So this environment variable here, it has as value the protocol, in this case also the TCP :/ and the IP of the source container, colon, the port being exposed. So remember that the port, the internal port that we have exposed at the source container, the second source container, the number was port 80, and that's the number used to construct these environment variables and not the external port number. It's the internal port number that's used here. So that's why the value here is TCP : / the IP of the source colon 80 and not 8080. 8080 would be the external port at the host system, but the internal port is 80. So the port used to create these environment variables is the internal port of the source container we are linking this target container to. So you already have identified these two environment variables according to its pattern. Now let's identify the alias underline env and underline the env name, the name of the environment variable declared at the source. So remember that we only declared one environment variable there, which was env1. So, and the alias is openlink. So openlink underline env underline env1. Openlink underline env underline env1. So here it is, the one and only automatically generated environment variable at the target, generated from the environment variable declared at the source, is this one, because we only have there one single environment variable declared. And the value here is the value of that same environment variable at the source. So here is the third environment variable we have identified according to the patterns here at the documentation. And now the only ones that we're missing is the ones that have as base pattern the alias underline port underline the port number underline protocol and the address, port and proto words or suffixes. So as we know, in our case it would be the alias name is openlink underline port underline, the only port we're exposing is port 80, so openlink underline port underline 80 underline CP. So here we have openlink underline port underline 80 underline TCP and the words address, port and proto. So here is one of them, openlink underline port underline 80 underline TCP underline address. So here is the environment variable for the address of the source container, the IP address of the source container. Also here we have openlink underline port underline 80 underline TCP underline port for the port associated to that link connection, which is the internal port, port 80, and not the external port to which we map it, that internal port, which will be 8080, but it's not the case. The port used here is the internal port inside the container that is mapped to the outside port at the host. And the other one is openlink underline port underline 80 underline CP underline proto with the value of the protocol used, which is TCP. And actually that base pattern also is a variable here created, which is this one, without the address, without the proto, and without the port, but only with that base pattern here. The alias, which is openlink underline port underline 80 underline the protocol TCP, without the suffixes address, port and proto. And for this the value is actually the same of the value of this alias underline port, which is TCP : / the IP of the source container / 80, with the difference that if you remember, this base environment variable here and the other three that derive from it is 4 for each port, and this alias underline port is only one single variable taking the lowest number port. So this alias underline port will always be only one single environment variable with only one of the ports despite any number of ports published at the source, while this base pattern variable here, as well as the other three that derive from it, the address, port, and proto, will be multiples to any number of published ports exposed at the source. If you have 10 ports exposed there, you would have one base pattern variable here, along with 3 other variables derived from it. So you would have 4 times all of those ports exposed, but only one taking the alias underline port with the lowest number port. So I guess this is it. Let's now clear everything. Sudo docker container remove -f $ open parentheses sudo docker ps-a-q. Let's remove the images. For images, you do not remove with rm, you remove with rmi, just remembering that. The volumes, we have not created anyone, and the networks, we only have those 3 created by default by Docker. So, and one last information here is that the links that we create, remember that they are stored not with the networks, but inside each container. So actually, specifically at the recipient container and not at the networks. So these 3 networks here, they have no information about that link that we had created before, and that has been erased along with the container, the recipient container that we erased. So all clear. Now the only thing that remains to be tackled here at our practice lecture about networks is the /etc/host file. And with this, we'll finish this lecture. So let me read here for you. In addition to the environment variables that we have already discussed, their patterns of creation and value set or discovery, and we have also demonstrated at our terminal. In addition to that, Docker also adds a host entry for the source container to the /etc/host file. So it then gives a sample demonstration of the content of this file, which includes not only the IP for that file, for that container ID, but also in case that recipient container does have a link to a host container, also this file at etc/hosts will also contain the IP for the source along with the link alias name, as well as the ID of the source and the name of the source container. So basically is that when we create the link, also it's created another line here at this file /etc/hosts at the target container or at the recipient container, having not only the IP of the target container along with its ID, but also the IP of the source container along with the alias of the link and also the ID of the source and the name of the source container. So this information will be available at this file in case you want to get through this etc/hosts file and always updated information about the source, either its IP or its ID, its name, or the alias of the link. So you can see two relevant hosts entries. The first is an entry for the web container that uses the container ID as a host name, and the second entry uses the link alias to reference the IP address of the DB or source container. So in addition to the alias, you provide the linked container name, if unique, from the alias provided to the link parameter, and the linked container's hostname are also added to /etc/host for the linked container's IP address. So if you wanna from inside the target container, if you wanna ping the source container, you can do that either by using the IP or the alias name, or even the source ID or source names. And by pinging, we can assume any connection that we would like to do from inside the target container to the source container, for example, from a springboot application inside the target container to a mysql container at the source container. So you can see now what all of this has to do with our original applications and our original containers that we were managing, and why I had to specialize all the learning about networks and links before explaining to you the best ways to use links for our containers, as well as how to use not only default networks but also user default bridge networks along with Docker Compose, which is what we're gonna see in the next lecture. So for this lecture, it's this. If you want to read everything that we have seen in these 4 Docker documentation sections, you simply go to these paths and you can find it there at the Docker site. The part about the drivers available by default, the part about the differences between default bridge network and user-defined bridge network, the part with the implementation of those examples for testing the connections between some number of containers and the default bridge network and user-defined bridge network with and without links, and finally the part about links when using default bridge networks and all the characteristics that links give us for adding to the features already available at the default bridge network, which are the DNS resolution and the environment variables automatically created from the information of the source container and the creation of those variables at the target or recipient container side, so that the target container will be able to use those information, for example, when configuring an application.properties file for the connection between those 2 containers, linked containers, as well as lastly the etc/hosts file, where you can have some of those informations always updated at the target site. So that's it. Next lecture will be refactoring our running expressions or statements that we had used with our original containers, with the containers we were working before we started seeing networks in a more specialized way. And we'll see how to better use links with default bridge networks, and also how to change that for using user-defined bridge networks and sharing those data not through automatically created environment variables, because we will not be using links anymore when changing our networks to user-defined bridge network, but we'll share the same way by using Docker Compose, as we also could share by using volumes with some common configuration file, or if we were using Swarm. So see you next lecture, and thanks one more time for your patience, and I hope you have learned a lot with these network lectures. So see you soon.